Hello, my name is Peter Hall,
I'm David Thompson.
and this is the Distributed Spacecraft Ad Hoc Communication Project. So what is ad hoc communication? Ad hoc communication is a way to decentralize communication and remove reliance on centralized access points or existing infrastructure. This is facilitated by having nodes send packets of information to neighboring nodes. Nodes that are not the intended recipient can forward the information then to their neighbors until it reaches the desired recipient. This can be streamlined using protocols such as the Ad Hoc On-Demand Distance Vector Routing Protocol, or AODV, which was pioneered by Charles E. Perkins and Elizabeth M. Royer. AODV has each mobile host act as a specialized router that obtains routing information on demand.
The problem we are addressing in this project is replacing the current method of space exploration, which is very costly. The old method requires each satellite to receive constant commands sent from Earth and then transmit data back to Earth in order to operate. In this project, we are instead enabling a swarm of spacecraft to communicate and cooperate amongst themselves and operate more autonomously. Since these small spacecraft are not receiving commands from Earth, they are heavily reliant on communicating with each other, and direct communication between two satellites in space may not be realistic. This is why the AODV protocol is being used, which would allow satellites to pass messages to other satellites that they may not be in direct contact with. These drones are organized into subswarms with a leader. The leader communicates with other drone leaders, and they can transmit data to the smart carrier. The carrier transmits data to Earth and to the drone leaders. This algorithm will determine which spacecraft receives and transmits specific data. The purpose of this project is to test the application of AODV routing protocol to these small spacecraft. This is a Matlab simulation of the flight paths of the drones around an asteroid, the red being the carrier drone while the rest are subswarms of drones.
To simulate the satellites, we're using Raspberry Pi 3B Pluses. This is because they have access to AODV libraries, which makes them really easy to code and to use in testing. And additionally, they can be converted into drones using Navio 2 interfaces, and they allow for easy interfacing with other testing tools such as LEDs, LCDs, and other output devices. Additionally, the quadcopter base that we're mounting them on is the ReadyTosky S500 quadcopter to emulate the physical part of the satellite.
The first drone test was to make sure the newly built drones were able to fly. Two of the drones were able to follow the flight path given by the ground control. One of the drones had an ESC catch on fire. This could have been caused by the wires connecting the ESC to the motor being bare metal at some places, causing the ESC to short, or the ESCs were just not calibrated. The ESCs were then replaced, recovered, and recalibrated. The second drone test was to test the drone programming used with autopilot. The drone that burned out gave an error message showing bad barometer health. The other two drones failed to follow the flight path, most likely due to bad wind. The third test was again to see if the drones could follow the programming flight path. All of the drones had the error message showing bad barometer health. To try and troubleshoot the problem, we switched out hardware parts of the drone, made sure there was no metal around when flying the drone. To see if it is a software issue, we commented out specific code on the Raspberry Pi that might be affecting the barometer. Currently, we're wiping each Raspberry Pi and reinstalling the software on it to see if the error message goes away. A problem that the previous undergrad group had was that the part connecting the legs and the body of the drone kept breaking when it landed due to the legs going outward and inward. As a solution, we created a 3D clamp to clamp a support arm between the legs to prevent them from caving in or spreading apart, which is what kept causing the breaking.
So beginning the ad hoc tests. The ad hoc tests were proposed to help configure the Pis so they would correctly route packets. There were 6 proposed configurations. These configurations changed how the range of the Pis overlapped and affected the routes of the packages being sent. The Pis would then light up different colored LEDs depending on what type of action the Pi is taking, if it's routing it to different Pi, if it's sending a hello message, or if it's processing/sending a packet. Some test specifics. The Raspberry Pis are numbered 1 through 5. In each configuration, Pi number 1 is attempting to send a message to Pi number 2. Configurations 1 and 2 both had static arrangement of pies, while configurations 3 through 6 had pies being inserted into the arrangement and removed after the beginning of the test. The LEDs would then be observed before and after each change in the system. Depicted on the right is arrangement 2, which notably is missing pie number 2, and is meant to show how a system will react to not having the end node. The preliminary ad hoc tests, which were done before David and I were on the project, were originally tested by Zach Smeton and Hayden Sathers. The first two arrangements interacted exactly as expected, but the third and fourth arrangements ran into several problems. First of all, the first and second Raspberry Pi would randomly connect and communicate over distances which were not expected, such as much greater than a football field. The first and third, or the second and third, wouldn't be able to communicate despite very short ranges. The height of the Raspberry Pis from the ground had a significant effect on the communication. When they're on the ground, it would end up interfering with the communication and make it so that they wouldn't communicate at all. Then finally, the lights on several of the Pis indicated that packages were being forwarded, but none were being received. These problems became worse in the fifth and sixth arrangements, which incorporated more of the Pis, and it came to a point where the results were almost unintelligible. These were likely caused by two issues. First of all, the code receiving and sending packets was only running once a second, which would cause the Pis to miss several packets. Zachary was able to fix this issue with some changes to the code, changing it so the packets were received every iteration of loop, which is much more than 1 second. The second problem was the logistics of the real-world networks, making the arrangements almost impractical, which was further worsened by the simplistic interface of the LEDs, making seeing the actual results much more difficult. Preparing for future tests. Since the preliminary tests, several of the Pis have been converted into drones using the Navio 2 system. While the Navio 2 system is attached, however, the Pis can no longer support LEDs, LCDs, or other output devices. This makes them very impractical to use for the ad hoc tests. This made it so that we had to purchase additional Pis. Initially, we purchased several Raspberry Pi 4s, and were set up to continue these tests. But a change in the operating system between the 3V Pluses and the 4s rendered the AODV libraries completely useless. This resulted in purchasing additional 3V Pluses and configuring them to be suitable for the tests. Additionally, the testing code was altered for the use of LCD screens. Moving forward with the ad hoc tests, we'll attempt to solve the problems of the previous test. LCD screens will replace the LEDs so that the packet routing is more obvious. The Pis will be elevated off the ground to mitigate the communication errors that arose, and more of the research team will be present, ideally enough to have each Pi monitored and moved individually. These steps should help both to gather more information on why the communication errors were occurring and to prevent some of those communication errors.
Going forward with the drone testbed, once we get the error messages out of the way, we will test using the DroneKit software with one drone at a time. Then we will fly multiple drones at a time to test the AODV protocol on simulated missions by collecting data from the drones.
Thanks for watching.